Right, in this section we'll talk about, we'll actually give an example of a chi-square test for goodness of fit. So for these chi-square tests, either we're doing a goodness of fit test or we're doing a test for independence. Okay, so goodness of fit is pretty much we're saying, hey, the outcomes we observed should come from this following distribution. So it could be like a uniform distribution, a binomial distribution, or some probability distribution function that we've seen in the past where we know the probability of each outcome. And given a sample size, or given a number of observations, we can say, well, this percentage should be here, this percentage should be there, so on and so forth. And then we compare that to the reality for goodness of fit. So as far as hypothesis test goes, I mean, really it's the business as usual. I mean, we've done plenty of hypothesis tests for now, and really the steps are always the same. Okay, the big difference for the hypothesis test for goodness of fit, they're always the same, meaning here the null hypothesis is that the probability distribution is the same as the proposed variable. So we're just saying that it's 47.4% chance red, 52.6% chance not red. I mean, we're just saying it comes from some distribution. Okay, so in here the big difference compared to previous examples is that there's no mu's or p's or no equal signs. We're just saying, hey, the distribution is this. Okay, and the alternative is just that the distributions are different. Okay, so there's no greater than, less than. It's just say, hey, maybe they come from a different distribution. Okay, here prepare. I mean, of course, we have a random sample, independent measurements, and the expected count is at least 5 in each cell. Okay, so that's what we mean by large sample size. So remember the first two is just make sure that our data is not biased, right? And because if our data is biased, then it's no good. Okay, our test is garbage. And then what this last thing does, the expected count, make sure that our sample size is large. Okay, so here, I mean, we could still have good data, but as far as the p-value that we're using, it could be very, very, very inaccurate. Okay, so that's what these are checking. And of course, compute and compare, find the p-value. Okay, so in this case, it's always this. It's the probability that if the null hypothesis is true, a chi-square statistic will be as big or bigger than the one observed. Okay, so there's no one-sided or two-sided. It's always going to be a greater than or equal to probability in computing the p-value. And as far as interpret, it's the same. Okay, this here can hold for any of the hypothesis tests that we discussed before. Okay, p-value less than alpha, reject the null hypothesis. P-value greater than alpha, then fail to reject the null hypothesis. Okay, so we revisit this example with the roulette wheel. So we say, is the roulette wheel balanced? Okay, we want to test this at alpha is equal to 0.01. Okay, so what we're saying is that if balanced, then the outcomes of 3 plays should be distributed as below. Okay, so pretty much what does that mean? It means, okay, we're assuming that the roulette wheel is balanced, so therefore each outcome is equally likely to occur. Right, so we have 18 plus 18 plus 2 total outcomes. Each of these outcomes is equally likely to observe. Therefore, the probability of red, okay, is roughly equal to 18 out of 38, which gives us 47.4% chance that it will be red. Okay, but we're not doing just one game. We're gonna bet on red 3 times in a row. Okay, so what we want to know is, well, what are the chances that it wins 0 out of 3, 1 out of 3, 2 out of 3, 3 out of 3? And of course, we're assuming that each outcome is equally likely. So we're kind of saying here that this roulette wheel is perfectly balanced, right? It's working the way it should be. Okay, because if my numbers are off from what I expect, then maybe my roulette wheel needs some repair, all right? Or maybe it's been sabotaged some way. Okay, but anyway, so here we have these results here. So we calculated these before. And of course, you did this one in the last exam. Okay, but we get 14.6%, 39.3%, 35.5%, 10%. Okay, so this is saying the probability of winning 0 out of 3, 14.6% chance, 1 out of 3, 39.3% chance, 2 out of 3, 35.5% chance, 3 out of 3, 10.6% chance. So you've done these on the test, and so that's why I don't get into how I create these, but you are more than capable of determining how we do that. So now I go and we observe the data. Okay, so what I'm going to do, I'm gonna do this strategy 50 times, meaning I'm gonna bet on red 3 times. and record the number of reds. I'm going to repeat this 50 times. Okay, so what I'm going to do is I'm going to compare my expected counts to the observed counts. Okay, so my expected counts, well, if it's balanced, 14.6% chance of 0 wins, that means 14.6% of the 50 should be 7.3. Okay, and we do the same for each one. Okay, my expected counts, I kind of explained these in the last video here. Okay, but once again, I mean, 39.3% chance we have 1 win. Therefore, if we play 50 times, 39.3% of these 50 games, I should win 1. Okay, and that's saying so roughly about 19.65. So remember, these are like expected, they're averages, so it's normal to see decimals here. Okay, and then we do 17.75, 5.3 here. Okay, so these are my expected counts here, and they're all greater than 5. So that's a good sign. Okay, now I actually play the game and I observe, well, actually I have 10 times I won 0 out of 3. 14 times I won 1 out of 3. 17 times I won 2 out of 3, and 9 times I won 9 out of 3. Of course, I won a little bit, I lost 3 in a row a little bit more than often, but also won 3 in a row a little bit more often. But obviously these numbers are different. Okay, these numbers are different. Okay, but are they significantly different such that we're going to conclude that this wheel needs repair, right? Or we need to figure out how it's sabotaged, right? Or is it possible just by random chance that these are true and we observe outcomes like these, right? Because remember, these are like average, right? These are like average, right? So if I were to play 50 games and another 50 games and another 50 games, all these observed, they're going to change. Okay, they're going to fluctuate, they're going to vary due to the random nature of the wheel, right? So these values may be a little high, a little low, a little high, a little low, a little high, a little low, a little higher than low than what's expected, right? But what we want to know is it's significantly different, combined total. So what we do here is, well, before we go on to find our p-value and to use this data, we need to make sure that the data we have is any good. Okay, so I mean random sample. So I say, yeah, we have a random sample 50 plays of 3. Okay, but the 50 that I played, we just had a random sample of 50. Outcomes of the roulette wheel, those are obviously independent. Okay, the outcome of one spin does not depend on the other. Okay, so what these two are guaranteeing, as they do for all the other hypothesis tests we're dealing with, they're making sure that your data is not biased. Okay, if your data is biased, then it means because your data is biased, then it's no good. Okay, just give up. Your data is no good. Okay, now what these are checking, the expected counts, this is checking sample size. So my expected counts, all of these are larger than 5. So that means is that your p-value is a good estimate. Okay, how we're calculating the p-value, we can rely on that number. Okay, same thing with all the other ones where we're checking sample size. I mean, really, we're checking whether or not our p-value is accurate and reliable measurement. Okay. So compute and compare. Okay, so what I do is I find the chi-square test statistic. All right, so for each cell, okay, for each outcome, I compare what I observed to the expected, square it, divided by expected. I do the same for each cell. And what I get is a chi-square test statistic of 5.89. Okay, and my degrees of freedom here, well, they're 4 minus 1. So for goodness of fit tests, I mean, as far as how we find degrees of freedom, usually degrees of freedom, they're equal to the number of cells, right? So that's like each category minus 1. Okay, minus 1. That's usually how they're found with these with the goodness of fit test, right? So my cells here, well, there's really 4 outcomes, right? There's 4 cells, right? Because 1, 2, 3, 4. Okay, 4 cells. So I did 4 minus 1. That's usually how we find it, though not every time. Sometimes we need to estimate something with the data, so that's when it would change. But in general, the degrees of freedom are number of cells minus 1. Okay, it's not 50 minus 1. That's not our sample size minus 1, but it's the number of cells minus 1. So we have 4 cells minus 1. So that's the big difference between degrees of freedom in dealing with the population mean and degrees of freedom in dealing with these categorical variables. Okay, here we're counting the number of cells, right, minus something, whereas in population mean mu, we're doing sample size minus 1. Okay, so just keep track of that difference here. Okay, this is number of cells. Okay, so we have 4 minus 1. Okay, so now what we want to do here is calculate this. Okay, so we find the p-value. Okay, so remember the p-value here, it's probability of observing my test statistic and larger values. Okay, okay, degrees of freedom are 3. Okay, so probability of observing this, assuming that the null hypothesis is true. Okay, so assuming that the wheel is balanced, okay, assuming that the wheel is perfectly balanced, then what is the probability of observing my chi-square test statistic of 5.89 and larger values? Okay, so remember here when doing goodness of fit or independence, it's always going to be the upper tail, okay, the p-value. Okay, okay. So here we get 11.7. So I mean, what we're saying is that assuming the null hypothesis distribution is true, assuming that the wheel is perfectly balanced, there's 11.7% chance of observing our test statistic of 0.58 or bigger or larger. And since 11.7% is larger than 1%, we failed to reject the null hypothesis. Okay, so it means at a 1% significance level, there's not enough evidence to conclude that the roulette wheel is off balance. Therefore, we can trust our probabilities found in our last exam. Okay, and furthermore, we could say, hey, we don't need to repair this roulette wheel. It's perfectly fine in balance. Okay, so we can leave it alone. Okay, but this is just an example of how we do a chi-square test for goodness of fit. Okay, and that will conclude our talk for today.